Let's talk about separable differential equations. Separable. That's quite a mouthful, but anyway, a separable differential equation is a first-order differential equation where the expression for dy dx, so the derivative of y with respect to x, can be factored into a function of x multiplied or divided by a function of y. So we can actually separate the variables into a function of x and a function of y. Now, whether these two functions are multiplied or divided, that doesn't really matter as long as we can separate them. So dy dx, if we can separate all of the x's into a function of x and all the y's into a function of y, and they're either multiplied or divided, and of course if they're divided we have the caveat that f of y cannot equal 0. If we can do that, what's really useful is that we can actually separate, thus the name separable. We can separate the two functions and place them with the appropriate differential and then just integrate both sides. So I took this one, for example, I took the quotient. So if we have d of y over d of x equals g of x over f of y, we can multiply both sides by f of y and both sides separate the differential, multiply both sides by dx. And then we can integrate both sides of this equation and we have two integrals. And we can integrate both sides of this equation and solve for the differential equation, solve for the function that would satisfy this. Sometimes we write that function implicitly, sometimes we're able to write it explicitly. All of that kind of depends on what this form is and if we can actually solve for it explicitly. So we'll talk about that as we're doing the examples. But the general idea of separable differential equations is that we can separate the variables into two functions, one a function of x, one a function of y, separate and then integrate. So one thing to note here, because we are going to work with different variables, one thing to note is that this theory was written in terms of x and y, but the variables can be anything we want or we need to work with, and we'll show that in the examples. So let's take a look at a couple examples. This is also a nice place for us because we are going to be doing integration. So it's a nice place as we're coming to the end of the semester to practice our integration techniques as well. Okay, so let's take a look at these two examples, possibly get 3 on this video, we'll see. So let's find the solutions to these differential equations. If there's no initial data given, then we're just going to be finding the general solution. Now, if initial data is given in any of our examples, which it will be in some of our examples here, then we will find the specific solution and use the initial data to do so, to find the constants. So here's 2 examples where I just wanted to mention, right, we can use any variables we want. So notice here that we're working with t and y prime of t. So the variables that we're working with here are y and t. And this y prime of t right here can be expressed as dy dt. We're taking the derivative of y with respect to t. Whereas over here, we're working with x's and w's, and we have the differential equation. We have the first order differential equation here. We have dw dx. So we're working with w's and x's, and we're trying to solve for y as a function of x. And here we're trying to solve for y as a function of t for a solution. Okay, so just wanted to mention my little note on the previous screen where I said, whatever the variables we're working with, we can adjust that notation that we were working with on the first screen, that we defined on the first screen. Okay, so I just zoomed in here, and this is the function that we're trying to find. We're trying to find a solution to this differential equation where t to the negative 6 times the derivative, y prime of t, is equal to 3. So I'm going to rewrite it, now that we've sort of identified what we're looking for. T to the negative 6 dy dt equals 3. And keeping in mind that I'm trying to solve this differential equation for a function of t. We're trying to find y as a function of t. If we can write it explicitly, or we might have to write it implicitly. We'll talk about that as we go. So this is definitely a separable equation. We could write this as 1 over t to the 6th. The t variables are all together. Dy dt equals 3. So it is definitely separable. There is actually only a constant. There's not even a y here. So we're able to separate the t's and the y's. And therefore, when I multiply both sides, t to the 6th, t to the 6th, we're going to end up with dy dt equals 3t to the 6th. And I'm going to separate the differential as well. So I'm going to go ahead and do that in one line here. So we're going to get dy equals 3t to the 6th dt. Now I can get in here and I can integrate both sides of this equation. Now the integral of y The integral of dy is just y, because that's 1 times dy. And the integral of 3t to the 6th is 3t to the 7th over 7 plus c. And that is my solution. Now, I'm pausing for just a second because I was looking at it real quick, but that is already explicitly. We are able to write that explicitly. As I said, if we can, we'll do that. If not, we'll write it implicitly, just as a relationship between y and t, but we can explicit solution here. We can actually write this y as a function of t equals 3/7 t to the 7th plus c. Now, that is, of course, just a general solution. We didn't have any initial data. Given any additional data, we would have been able to find that constant. But this is just our general solution to that differential equation. And there's our answer. So we separated the variables, integrated both sides, and then solved, if we could, solve for it explicitly. And given initial data, we would have also solved for that constant. Let's take a look at another one. Now, on this example, we can see that we've got again, a differential equation, dw dx, and we are wanting to solve for w. We want to find a solution to this differential equation, find a function w of x that would satisfy this differential equation. So again, this one we've got to do a little bit more work. That first one was pretty easy to separate. This one we might need to do a little more work, but it is definitely separable. So as I'm looking at this, I'm seeing that I could bring my w's to the left side and my x's to the right side. So to do that, I'll go ahead and divide, grab my red pen, go ahead and divide by x squared on both sides. And while we're at it, let's also divide by the square root of w. So if we divide by the square root of w, we end up with 1 over the square root of w dw. dw dx, we'll separate the differential in just a second. And then we've got 6x plus 4 over x squared. Now what we can do is we can separate that differential. We could bring the dx over here with our function of x and leave the dw on this side. So I've separated, notice I've got my w's on the right side with respect to w, and I can integrate on the right side. My x's have been moved over to the right side, and I can integrate with respect to x. So let's go ahead and do that now. So now we can integrate both sides of this equation with respect to their respective variables. Now to do that, let's go ahead and do just a little simplification. Let's write that as w to the negative 1/2 dw. And on this side, let's go ahead and write that it is a fraction, it's a rational function, but let's go ahead and just rewrite it as 6 over x plus 4 over x squared dx. And that 4 over x squared, I'm even going to write as 4x to the minus 2, so that I can use my power rule. 6 over x would be 6 times 1 over x, which is the natural, when we integrate, the natural log of the absolute value of x. And so we'll go ahead and rewrite those, just getting ourselves set up for the integration. Now when I integrate w to the minus 1/2, I'm going to get w to the 1/2 divided by 1/2, which is the same as multiplying by 2. Now I get a plus c there, but I'm going to go ahead and add it to the c that I get on the right side, so I'll have just a single c. So I get 2w to the 1/2. Now on this side I get 6 times the natural log of the absolute value of x, minus I get 4x to the negative 1, and then I divide by negative 1, which is why I got the minus 4. Now I will have an integration constant on that side, so I'll have plus c. There's actually an integration constant on both sides, but I just combined them into one single c here. Now this is a solution, so this is an implicitly defined solution right here. But this particular one, it's giving me a relationship between x and w. But I could actually solve, this is one, again, like the last one, where I could actually solve for, the other one was very easy to solve for the variable we were looking for as a function of the other variable. In this case, though, we can also solve for this. Remember, we were thinking about solving for w as a function of x, and we can actually do that here. And so let's just go ahead and clean this up and solve for this explicitly. So we've got our implicit solution. It's an implicitly defined solution, but let's go ahead and get an explicit solution. So I'm looking at this and I'm thinking, okay, if I want to solve for w, I'm going to divide both sides by 2 to start. And then I've got w to the 1/2, which is the square root of w. So the square root of w is equal to 3 natural log of the absolute value of x minus 2. I'm going to also drop that x down, 2 over x, so I don't have a negative exponent. And then I get c divided by 2. Now it's kind of funky, right? Because it's just this generic constant. It was actually the sum of 2 integration constants. And now we're taking that integration constant, we're dividing by 2, but it's still just a constant. So I'm going to erase that. Technically it is half of what we had right above, but it's still just a constant. And we don't know what it is yet. If we knew what it was, if we had some initial data, I would have found that c right here. So you could have found that initial data right up here if you had that. You could have found that constant if you had some initial data. So if you had some initial data, you could use it to find that constant, but we're just writing it as this generic constant. So I'm going to just continue to leave it as c, even though I've divided it by 2. Okay, that was a long explanation for why I kept that as c, but that is why I'm doing it. All right, now we're still trying to solve for w, to write it explicitly as a function of x. So let's go ahead and square both sides at this point. Now we have w as a function of x is 3 natural log of the absolute value of x minus 2 over x plus c squared. And now, because we were able to, we have expressed this as an explicit function of x. W is an explicit function of x. So just kind of showing you the two different types of forms, explicit solution, where we have w as a function. We were able to do it, so we wrote w as a function of x. Okay, let's look at one more example. So we've got dy dx equals 3e to the x minus y in the exponent. Now, the question might come up, is this separable? Can I separate this? Can I separate? Question mark. And we can separate this. We'll have to use some rules of exponents, but we will be able to separate this. So yes, we can separate this. The other thing that's given here is some initial data. So we'll be able to find our constants that we get as we're integrating. So there's also some initial data given here. So we'll be able to use that to find our constants. So let's go for it. So let's get in here. Let's use some rules of exponents that say that when we have e to a sum or a difference, we could write that as, or any base, in this case it's e to the x, e to the negative y. So we could actually write this dy dx as 3e to the x over e to the y. And look at that, we are able to separate. We separated. So we were able to separate this, which means it's a separable differential equation, and now we can separate it into two sides of the equation so we can integrate. So I'm going to multiply both sides by e to the y. So e to the y dy dx equals 3e to the x. I'm going to separate also the differential so I can integrate both sides. So we'll put the dx over here with the x. We're going to integrate both sides, and they're both exponential functions. So e to the y equals 3e to the x plus c. So we'll just integrate both sides and we get our relationship between x and y. Now again, this right now is an implicit relationship between x and y. So if I wanted to solve for y, I would have to isolate it. So let's go ahead. We can do that. We can take the natural log of both sides. So when we take the natural log of both sides, we will get y equals the natural log of 3e to the x plus c. And this is now a function of x. So here is our general solution, and it is an explicit relationship. Y is a function of x. So here's our general solution, which if we didn't have any initial data, we would highlight that and be done. But since we have some initial data, let's come back up here. Since we have some initial data, let's find that constant that we have. So y of 0 is the natural log of 3e to the 0 plus c, and that has to be equal to the natural log of 9. So the natural log of 3 plus c equals the natural log of 9. And so when we take the natural log, when we see that natural, I have an extra parenthesis right there. When we see that, we could exponentiate both sides and we would get 3 plus c equals 9. So my constant has to be 6. And now, given that initial data, I can write my function, my specific function that satisfies this differential equation. Y of x is the natural log of 3e to the x plus 6. And that is my solution to this differential equation, which has initial data or initial value problem.